And finally, a quantitative variable. After all those reds, blues, and greens, a few numbers. You have to forgive me, I get excited by numbers. I'm a statistician, what can I say? Right, so I'm going to start by introducing you to a kind of quantitative data set that I have to analyze every single term, and that is the set of scores of my class. So every term I have midterm scores, quiz scores, final scores, and I really want to know how my students are doing. So I want to know what the distribution looks like. So here are the scores of students in my most recent class. It was a graduate class, and these are their final scores. So you can see I've arranged them in increasing order. Somebody got 48, the next one was close to 60, and so on. So already I can see they did okay, but I don't know, how well the best person did in the class unless I write them all down, the scores. And so I've done that, but I've done that in an interesting way. Here we go. Now take a look at that picture. Some of you may have read something like this before. If you haven't, you can see clearly that this 48 is the 48 that was the lowest score in the class, and then this 59 is from here, and then there are all these things, the 60s, and this looks awfully like the 60s up here. And so how do you get it? Yes, you figured it out. There's 63, 63, 63, and 67, and what has happened is that I have been lazy. I just don't want to write that 6 every single time. So I've written 6 as the leading digit once, and this bar tells me read this as 63, 63, 63, and 67. And so you can see that the next score in the class was 70, and there's another 70, and another 70, and then 72, and so on. And so now you have a picture of the scores of the entire class. And you can see somebody got 100. I told you this was a graduate class, right? This person was a second-year undergraduate. It's just dazzling. This picture has a fanciful name. It's called a stem and leaf plot. This vertical part is the stem, and these things hanging off here are the leaves. And the person who came up with this name is the person who came up with this idea of summarizing data in this way, and his name is John Tukey, one of the great American mathematicians, computer scientists, statisticians, worked in Princeton roughly 1940s through 1980s, and he had a passion for understanding data visually and using very simple techniques to look at data visually. And this stem and leaf plot is so clever, very simple but so clever. It quickly gives you a sense of the distribution of the data. And here I can't resist telling you something else about Tukey. He's one of the first people, if not the first, to use the word software in a written article. He is almost certainly the first to use the word bit. Do you remember the zeros and ones we were talking about a couple of lectures ago? The basis of all computer programming. He came up with the word bit, and how did he come up with it? Well, he took the words binary digit, and he did not want to write this stuff in the middle. He just took the B and the IT at the end, and there, bit, you have the essence of the meaning, and you haven't written a lot of extra stuff that you don't want to write, which is almost exactly what you're doing with the stem and leaf plot. Very interesting man, Tukey. Look him up, look up Wikipedia. The man used to collect murder mysteries. Very interesting. Look him up. But now I must discipline myself and get back to work. So here's our picture again, and you can see that it's a nice graphical representation because you can see a curve. There it is. There's a curve of scores. There are a few problems with the interpretation of this picture because the difference between 48 and 59 is 11 points. The difference between 59 and 63 is 4 points, and on the picture it looks the same, which is a little bit disquieting, but still you get a sense of how the class did. The bulk of the people in the 70s, 80s, and 90s almost evenly distributed in that range, though not, of course, not entirely. So this is a easy picture to draw and a quick way of getting a sense of what your data are doing. Let's take a look at the good points of this picture. Points in favor. Number 1, easy to create. We've seen that, really easy to do. Number 2, retains all of the data. I believe I had 28 students in that class and all of their scores are here. I haven't lost anybody. I haven't really summarized. So when you are in a class and you've taken an exam, ask your instructor for a stem and leaf diagram of the scores, because then you will know exactly where you are in the class. For example, if you got 82, you will know exactly how many people scored above you and how many people scored below. That said, there are some problems with this diagram that some of you may have been thinking about already. For example, what if the scores ranged from 0 to 1,000? Some people have grading schemes where it's possible to get, hundreds of points and thousands of points. Then what would you do to make a stem leaf diagram? Well, then you'd have a very long stem, would you not? And you may not want to do that. You may not want to use this method when you have a vastly a data set that has a very wide range. So points against, not so convenient for many data sets. If you have a data set where the numbers are all multiples of 7, then you may not want to break them into tens, and so on. And another problem is that it retains all the data. And yes, I know we said that was a good thing, but it is also a bad thing. Because imagine a class that's bigger than my class of 28. Imagine our class, for example, Stat 2.1x. I've got, what, over 40,000 students? If we make a stem leaf diagram of all of their scores, then the 80s or any of these rows will start here and they will keep going in thousands and thousands and thousands and thousands, and they'll go all around the world, and you really don't want that level of detail. So while this stem and leaf plot is a wonderful way of summarizing simple, modest data sets, for larger data sets, you might need a bit more technique.